Hello. I've made three previous videos. The first two were the first and second half of chapter one of A Brief History of Time by Stephen Hawking. I then moved on to the beginning of chapter one of A Universe from Nothing by Lawrence Krauss. Seems to me I moved on a little early. And here's why. If you look at chapter one, for Universe from Nothing by Lawrence Krauss, it starts off with early in 1916, Albert Einstein had just completed his greatest life's work, a decade long, intense intellectual struggle to derive a new theory of gravity, which he called the general theory of relativity. This was not just a new theory of gravity, however, it was a new theory of space and time as well. And it was the first scientific theory that could explain not merely how objects move through the universe, but how also the universe itself might evolve. That's 1916. It further goes on to discuss a priest by the name of Georges Lemaitre in 1927 and Pope Pius XII in about 1951. For more on that, you can look at my first video. And it's going to go further if I keep going into Henrietta Swan Leavitt of 1913 and Edwin Hubble in 1925. So before moving into all these 1900 scientists, I decided to check out chapter 2 of A Brief History of Time. And I did see that the happenings of chapter 2 do take place before the chapter 1 of A Universe from Nothing. So I'm going to continue with chapter 2 of a Brief History of Time by Stephen Hawking. Our present ideas about the motion of bodies date back to Galileo and Newton. Before them, people believed Aristotle, who said the natural state of a body was to be at rest and that it moved only if driven by a force or impulse. It followed that a heavy body should fall faster than a light one, because it would have a greater pull toward the earth. The Aristotelian tradition also held that one could work out all of the laws that govern the universe by pure thought. It was not necessary to check by observation. So no one until Galileo bothered to see whether bodies of different weight did in fact fall at different speeds. It is said that Galileo demonstrated that Aristotle's belief was false by dropping weights from the Leaning Tower of Pisa. The story is almost certainly untrue, but Galileo did do something equivalent. He rolled balls of different weights down a smooth slope. The situation is similar to that of heavy bodies falling vertically, but it is easier to observe because the speeds are smaller. Galileo's measurements indicated that each body increased speed at the same rate no matter what its weight. For example, if you let go of a ball on a slope that drops by 1 meter, for every 10 meters you go along, the ball will be traveling down the slope at a speed of about 1 meter per second after 1 second, 2 meters per second after 2 seconds, and so on. However heavy the ball. Of course, a lead weight would fall faster than a feather. But that is only because the feather is slowed down by air resistance. If one drops two bodies that don't have much air resistance, such as two different lead weights, they fall at the same rate. Galileo's measurements were used by Newton as the basis of his laws of motion. In Galileo's experiments, as a body rolled down the slope, it was always acted on by the same force, its weight, and the effect was to make it constantly speed up. This showed that the real effect of a force is to always change the speed of a body, rather than just to set it moving, as was previously thought. It also meant that whenever a body is not acted on by any force, it will keep on moving in a straight line at the same speed. This idea was first stated explicitly in Newton's Principia Mathematica, published in 1687, and is known as Newton's first law. What happens to a body when a force does act on it is given by Newton's second law. This states that the body will accelerate or change its speed at a rate that is proportional to the force. For example, the acceleration is twice as great if the force is twice as great. The acceleration is also smaller the greater the mass, or the quantity of matter of the body. The same force acting on a body of twice the mass will produce half the acceleration. A familiar example is provided by a car. The more powerful the engine, the greater the acceleration. But the heavier the car, the smaller the acceleration of the same engine. In addition to his laws of motion, Newton discovered a law to describe the force of gravity, which states that every body attracts every other body with a force that is proportional to the mass of each body. Thus, the force between the two bodies would be twice as strong if one of the bodies, say body A, had its mass doubled. This is what you might expect because one could think of the new body A as being made of two bodies with the original mass. Each would attract body B with the original force. Thus, the total force between A and B would be twice the original force. And if, say, one of the bodies had twice the mass and the other had 3 times the mass, then the force would be 6 times as strong. One can now see why all bodies fall at the same rate. A body of twice the weight will also have twice the force of gravity pulling it down, but it will also have twice the mass. According to Newton's second law, these two effects will cancel each other out. So the acceleration will be the same in all cases. Newton's law of gravity also tells us that the farther apart the bodies, the smaller the force. Newton's law of gravity says that the gravitational attraction of a star is exactly 1/4 that of a similar star at half the distance. This law predicts the orbits of the Earth, the Moon, and the planets with great accuracy. If the law were that the gravitational attraction of a star went down faster with distance, the orbits of the planets would not be elliptical. They would spiral into the sun. If it went down slower, the gravitational forces from the distant stars would dominate over that of the Earth. The big difference between the ideas of Aristotle and those of Galileo and Newton is that Aristotle believed in the preferred state of rest. Which, by the way, Aristotle's right there. School of Athens by Raphael. In any case, the difference between Aristotle and those of Galileo, the ideas of Galileo and Newton, is that Aristotle believed in a preferred state of rest, which any body would take up if it were not driven by some force or impulse. In particular, he thought that the Earth was at rest. But it follows from Newton's laws that there is no unique standard of rest. One could equally well say that body A was at rest and body B was moving at constant speed with respect to body A. Or that body B was at rest and body A was moving. For example, if one sets aside for the moment the rotation of the Earth and its orbit around the sun, one could say that the Earth was at rest and that a train on it was traveling north at 90 miles per hour, or that the train was at rest and the Earth was moving south at 90 miles per hour. If one carried out experiments with moving bodies on the train, all Newton's laws would still hold. For instance, playing ping pong on the train, one would find that the ball obeyed Newton's laws just like a ball on a table by the track. So there is no way to tell whether it is the train or the Earth that is moving. The lack of an absolute standard of rest meant that one could not determine whether two events that took place at different times occurred in the same position in space. For example, suppose the ping pong ball on the train bounces straight up and down, hitting the table twice on the same spot 1 second apart. To someone on the track, the two bounces would seem to take place about 40 meters apart, because the train would have traveled that far down the track between the bounces. The non-existence of the absolute rest therefore meant that one could not give an event, an absolute position in space, as Aristotle had believed. The positions of events and the distances between them would be different for a person on the train and one on the track. And there would be no reason to prefer one person's position to the other's. Newton was very worried by this lack of absolute position, or absolute space as it was called, because it did not accord with his idea of an absolute God. In fact, he refused to accept the lack of absolute space, even though it was implied by his laws. He was severely criticized for this irrational belief by many people, most notably by Bishop Berkeley, a philosopher who believed that all material objects in space and time are an illusion. When the famous Dr. Johnson was told of Berkeley's opinion, he cried, "I refute it thus," and stubbed his toe on a large stone. Both Aristotle and Newton believed in absolute time. That is, they believed that one could unambiguously measure the interval of time between two events, and that this time would be the same whoever measured it, provided they used a good clock. Time was completely separate from and independent of space. This is what most people would take to be the common sense view. However, we have to change our ideas about space and time. Although our apparently common sense notions work well when dealing with things like apples or planets that travel comparatively slowly, they don't work at all for things working at or near the speed of light. The fact that light travels at a finite but very high speed was first discovered in 1676 by Danish astronomer Ole Christensen Romer. He observed that the times at which the moons of Jupiter appeared to pass behind Jupiter were not evenly spaced, as one would expect if the moons went round Jupiter at a constant rate. As the Earth and Jupiter orbit the Sun, the distance between them varies. Romer noticed that eclipses of Jupiter's moons appeared later the farther we were from Jupiter. He argued that this was because the light from the moons took longer to reach us when we were farther away. His measurements of the variations in the distance of the Earth from Jupiter were, however, not very accurate, so his value for the speed of light was 140,000 miles per second, compared to the modern value of 186,000 miles per second. Nevertheless, Romer's achievement in not only proving that light travels at a finite speed, but also in measuring that speed was remarkable, coming as it did 11 years before Newton's publication of Principia Mathematica. A proper theory of propagation of light didn't come until 1865, when British physicist James Clerk Maxwell succeeded in unifying the partial theories that up to then had been used to describe the forces of electricity and magnetism. Maxwell's equations predicted that there could be wave-like disturbances in the combined electromagnetic field, and that these would travel at fixed speed, like ripples in a pond. If the wavelength of these waves, the distance between one wave crest and the next, is a meter or more, they are what we now call radio waves. Shorter wavelengths are known as microwaves, they're about a few centimeters, or infrared, more than a 10,000th of a centimeter. Visible light has a wavelength of between only 40 and 80 millionths of a centimeter. Even shorter wavelengths are known as ultraviolet, X-rays, and gamma rays. Maxwell's theory predicted that radio or light waves should travel at a certain fixed speed, but Newton's theory had got rid of the idea of absolute rest. So if light was supposed to travel at a fixed speed, one would have to say that the fixed speed was to be measured relative to. It was therefore suggested that there was a substance called the ether that was present everywhere, even in empty space. Light waves should travel through the ether as sound waves travel through the air, and their speed should therefore be relative to the ether. Different observers moving relative to the ether would see light coming toward them at different speeds, but light's speed relative to the ether would remain fixed. In particular, as the Earth was moving through the ether on its orbit around the sun, the speed of light measured in the direction of the Earth's motion through the ether when we were going toward the source of light should be higher than the speed of light at right angles to that motion when we are not moving toward the source. In 1887, Albert Michelson, who later became the first American to receive the Nobel Prize for Physics. And Edward Morley carried out a very careful experiment at the Case School of Applied Science in Cleveland. They compared the speed of light in the direction of the Earth's motion, with that at right angles to the Earth's motion. To their great surprise, they found they were exactly the same. Between 1887 and 1905, there were several attempts, most notably by Dutch physicist Hendrik Lorentz, to explain the result of the Michelson-Morley experiment in terms of objects contracting and clocks slowing down when they move through the ether. However, in a famous paper in 1905, a hitherto unknown clerk in the Swiss Patent Office, Albert Einstein, pointed out that the whole idea of an ether was unnecessary, providing one was willing to abandon the idea of absolute time. A similar point was made a few weeks later by leading French mathematician Henri Poincaré. Einstein's arguments were closer to physics than those of Poincaré, who regarded this problem as mathematical. Einstein is usually given credit for the new theory, but Poincaré is remembered by having his name attached to the important part of it. And the next reading of A Brief History of Time, Chapter 2, will go into a little more on Albert Einstein.